Have you ever noticed that FG modules and representations look exactly the same? No? Just me? Well, what do I know? I don't even go to school. But hopefully, by the end of this video, you're going to see what I'm talking about. And also, possibly more importantly, I'm going to use this understanding to describe equivalent representations in light of FG modules. In an earlier video, we were talking about what it means for two representations to be equivalent, but I haven't brought that up in terms of FG modules, so we're going to clarify that by the end of this video. In the last video, I talked about how you can start with a representation and use that to create an FG module. You let the representation define your group action, and we'll come back to that in a little bit. But right now, I'd like to talk about going from an FG module and defining a representation. Just to remind you, an FG module is a vector space together with a group action. That's a way of multiplying group elements in vectors to give you back a vector, such that these 5 properties are satisfied. The multiplication is closed, the multiplication is a group action, and the multiplication is linear. Okay, so suppose we start with a vector space. Could be Cn, Rn, and let that vector space be an FG module with some finite dimension. Since the group action is closed and linear, and here I'm just labeling what of those 5 properties I'm using, right, from the definition that I just showed you, the action of any group element is an endomorphism. Endomorphisms of a finite dimensional vector space can be mapped to square matrices by picking a basis. Any linear map can be a matrix, but you have to be mapping from an n-dimensional vector space to an n-dimensional vector space. They have to have the same dimension for it to be square. And if it's closed, that means you're mapping from a vector space back to itself. So your domain and your codomain are certainly going to have the same dimension. So then the linear representation can be turned into a matrix, and we know that matrix is going to be square. Okay, so consider this map. Let's call it F. It takes in a group element and spits out a matrix. It's going to be n by n. And it's going to have entries in the array from our field F, the same field that our vector space is over. And all we're doing is saying, okay, take your group element and pick some basis B, and let that basis tell you how to turn your group action, which is an endomorphism, into a matrix, right? Multiplying by any group element is going to be an endomorphism. We just talked about how endomorphisms are always going to give us n by n matrices. And how do you do that? Well, you pick a basis. So this is going to be a map from G to GLNF. Now this is half of what we need for F to be a representation. A representation takes our group elements and maps them to GLNF, that's great, but we also need it to be a homomorphism. But for it to be a homomorphism, we need to know that the image of F, the matrices that it hits over here, is a group. Right now we have that the domain is a group, but the image, we don't know what matrices it maps to. We just know it's mapping to matrices. So let's check that that is in fact a group and that F is indeed a homomorphism, right? So this is what I was saying. F is the pick a basis map. So B is some basis of our vector space. If F is also a homomorphism, then F is a representation, right? That's what I was just saying. Using property 3 from our definition of what an FG module is, we know that the identity element of our group acting on a vector has to give us back that same vector. This is true for all vectors in our vector space. So if we pick a basis, this is going to be some matrix times V and has to equal V for all V in our vector space. This has to be true for every single vector. Well, there's only one matrix that does that. That is the n by n identity matrix. That means that regardless of what basis we pick, the identity element in our group has to be mapped to the identity matrix in GLNF. So that's good. We have that the image of F, right, the matrices that we get mapped to, includes the identity. That's one of the properties that we need for it to be a group. Okay, so far so good. So we also have the second property from our definition of a FG module. This is true for all vectors in our vector space. So we can drop this V over here. It's not dependent on which vector we pick at all. So if we pick a basis, we have this group element right here, right? It's a product, but that's just gonna be another group element. And then over here, we have the group elements being mapped first and then acting on V. Again, since this is true for all V, all elements in our vector space, we don't actually have to talk about the vector. And so we have that multiplying in the group before mapping is the same as mapping first and then multiplying after. So that's one of our properties of a homomorphism. That's good. But again, we still don't know that F maps to a group. We're still checking that, but we're almost there. If we let H be G inverse, if we plug that in over here, we have G times G inverse, that just goes to the identity, and then I just plugged it in. But we know that the identity element in our group gets mapped to the identity matrix. So we have G, after being mapped to the matrices by this basis, by this pick a basis function, times G inverse being mapped by the pick a basis function, gives us the identity. this guy is a matrix. This here is saying we take G, pick a basis, that maps it to the matrices. This is a matrix. It has an inverse. So that inverse exists and is equal to G inverse from our group and then mapped by the pick a basis function. So we showed that the image of our pick a basis function is actually a group. It has inverses, it has the identity, we have associativity. So we have that this map F maps from our group G to GL and F, and we have that its image is a group and F is a homomorphism between G and that group. So therefore F is a representation. What this is saying is no matter what FG module you start with, if you pick a basis, you can then always define a representation using your group action and that basis. So I've summarized that here. If you start working with FG modules and you pick a basis, you can use that to map your elements to the matrices. Right, that proof that we showed, you can always do this by picking a basis, and you can always create a representation from your FG module. We have constructed this. There's no FG modules that live outside of the representations. And in the last video, we started with representations, and we said, oh, well, that's just a matrix. We know how matrices act on vectors. If you let those matrices act on a vector space, it defines a group action. No matter what representation you start with, you can always create an FG module. You cannot find a representation that can't then generate an FG module. So this is why FG modules and representations really talk about the same things. You can't have one without the other, because when you start with an FG module, you're always free to pick a basis. There's no vector space that an FG module can be over that you can't pick a basis. You can always pick a basis for an FG module. You always have that freedom. And with a representation is going to have degree n, and you can always just have an n-dimensional vector space to have these guys act on. Right? Your representation is going to be over some field f and have some degree n, and you just look at the vector space v equals fn. So these two guys are really talking about the same things, just from slightly different viewpoints. So now that we see that representations and FG modules are the same thing, I want to talk about that last property of representations that I brought up, equivalence of representations, in terms of FG modules. I left that out because we needed that understanding of the connection before we could continue. So suppose we have two representations that are equivalent, rho and sigma. They're defined over some group. I'm not putting all the details in here. I know you guys are adults. And if you're a kid watching these videos, I mean, good for you. I mean, you don't want to know what I was up to at your age. So sometimes you're going to have to put the pieces together and realize that G is a group element. Little g lives in big G. And this is a representation of degree n, etc., etc. So we know that if two representations are equivalent, that this is the case. And in the video talking about equivalent representations, I reminded you that this is how you change the basis of a matrix. So we started with our representation, and we're going to let that define a group action on some vector space v fn. So then v becomes an FG module, right? We have a vector space, we have a group action. So then we know that there must exist a basis such that rho of g is equal to g under this pick a basis map. I keep giving them quotes, but it is a legitimate map, right? There's always a correspondence between representations and FG modules. You cannot have an FG module with a group action that doesn't give you a representation, right? Every FG module has some group action, and when you pick a basis, it's always going to give you a representation. And every representation, when you let it act on the appropriate vector space, is going to give you an FG module, right? There's a correspondence between these two. So substituting this into our equation here, we have that G under the pick a basis map has to be equal to this guy. Now if we just rearrange, right, I multiply both sides on the left by t, that's going to cancel out this, and we get the t over here. Multiply both sides on the right by t inverse to cancel that out, we get t inverse over here. Then we just define a new matrix. Just say S is t inverse and S inverse is t. Then we're going to have that sigma of G is equal to S inverse times this matrix G in some basis times S. But we already know that this is just how you change the basis of a matrix. So that's just going to give us G in some other basis. So we found that the map sigma of G is just equal to the pick a basis map for this new basis. And we have that sigma and rho define the same action on V and are therefore the same FG module. So what we see is that when you have two equivalent representations, what that means is when you let them act on the appropriate vector space, they're going to tell us the same information. They're just expressing it in two different bases, but it's the same FG module. They do the same thing to this space. So this is what felt like should be the case, but now we've actually concretely gone through things and shown that equivalent representations in a deeper sense, right, when we look at them in terms of acting on a vector space, are the same information. Alright, so that's it for this video. If you have any questions, make sure you leave them in the comments below. If you found this video helpful, please like and subscribe. And I'll see you for the next video. I think I'm going to be talking about permutation modules, whatever the heck those are.